Igor, the floor is yours. They always have to be somewhere you don't expect.
Ah, lights. Okay. Okay, so good morning, everyone. My name is Malgorzata Pajak, and I'm from Silesian University of Technology. I'm working in the civil engineering. My work is mainly based on laboratory investigations of big elements, big scale elements. So this is the part of our research that I would like to introduce you and show you that this is connected with the application of the fibers that we possess from the end of life tires, and we use it to strengthen the concrete. So first, some introduction. Where did how did this started? So first of all, in the last decades, they started to produce a lot of tires because of the worldwide need to travel around the world. So the tires, one example, the tires that were produced only in Europe in 2020 was more than 300 millions. So there are a lot of tires which are used after some time, and then you have to do something with them, yes? So when it's put on landfills, you can see here the example, it poses the fire hazards, yes? And also it's very dangerous because it's a breeding ground for the mosquitoes. So it may cause some diseases and so on. So generally the end of life tires shouldn't be placed on the landfills. So nowadays, it's about 4 million tires that are used and already are on the landfills. So there are 2% of the total global waste is connected with tires. So how it was, so there is a huge need to recover them. They do not degrade naturally, so we have to recover them somehow. So during the years, you can see here that at first, when they were invented, they were invented, and then they started the recycling rate was quite high. It was about 50% because the rubber was very, the high costs of the rubber. So it was, they had to recover it to get again the rubber. But then they invented some part of the tires could be replaced with the synthetic rubber, so the recycling rate decreased. And then after adding the steel cord, which strengthened the tires very much, then the problem started to be really big because it was very hard to grit the tires. So in that time in Europe, about 90% and 80% in USA and in Europe went to stockpile. And now, oh, sorry, not this way. And now we have around 90%. It is said that in Europe and USA we are recovering about 90% of the tires. But in truth, when you look at the statistic for the whole world, you can see that, for example, Nigeria has only 5%. Yes, they're recycling only 5%, and China not exceeding 40%. And China is especially important because they are they produce half of the total amount of tires. So their 30% is in truth a huge amount of tires. So our 90, let's say, it doesn't seems to be so good. So what about the whole world? How can we do the statistic for the whole world? So generally, not yet the fibers. Generally, they are used in the material recovery, about 42%, in the energy recovery, 15%, and in the civil engineering, it's only 2%. It's not too much. It could be much better because we generally are using the materials that could be the gum, the fibers, and so on could be used in it. So only 60% is recycled, and the other parts go to the landfills. So this is the example of the biggest in the world stockpile in Kuwait. So it can burn in every moment, and it is burning. So what's the composition of the tire? What can we use in our civil engineering? So first we have the natural rubber, the synthetic rubber. We have also some other components, but for us the most important is the steel wire. So the normal passenger car tire has about 11% of a steel wire, and for the truck tire it's about 20%. So we can, of course, when we are talking about recycle of tires, we can use it in the homemade way, so make some furniture to the garden, to the playground, but the tires generally are a very big opportunity for us to get the valuable resources. And what can we get from the tires? We can get the granulate, we can get the crumb, the fibers, but these fibers are the textile fibers, of course the fuel and the steel. So it is estimated that about 10 to 20% we can get from each tire. And it is worth to point out here that the steel is 100 recyclable. So and the steel is the most recycled material in the world, so we can always reuse it. There is only a huge problem how to divide the steel from the rubber granulate. It is the very big problem. However, in Poland there are some, also in Poland, because they are all over the world, there are some companies which are able to do it very cheaply. So nowadays it's not a problem. So we can divide the steel from the granulate. And how now it is used in civil engineering? So, of course, the retention walls, but let's say it's not too nice, but it can be used. The shedded tires, then they are used in a drainage basins, and it is the usage is quite common in civil engineering. Of course, some particles of the rubber can be placed into concrete. But the concrete is very brittle, so when we put too big parts on, or there are too huge amount of it inside of the concrete, it doesn't have any improvements for the concrete. So let's say we can do it, but it's not the best way of recycling. Of course, there are a lot of materials that can adapt the rubber. Modified asphalt, playground surfaces, isolation panels, so you can find it everywhere. So it is, but this is for the rubber, not for the steel. So what about the steel? Why can't we use it? We can use it in concrete. And where can we use it? So there is the fiber reinforced concrete. It is the kind of material that is used in many types of structures. First of all, I will show you the verses of the diagram from the material tests that are used to check the efficiency of the fibers in concrete. So when we have the beams, the small beams with a notch, when we do not add the fibers, it actually breaks. So the concrete without the fibers is completely brittle. It has a very huge strength, compression strength. But for the tensile, it's only 1/10 of the compression strength, so it's nothing. When only some tensile forces appear, the concrete just cracks, and that's all. That's why adding the fiber is very useful. So generally, we are adding the fibers to concrete. We are already doing it. So why can't we do it with the recycled fibers? So what are the advantages of using the fibers into concrete? Here you have the example of the results from the test, from this 3-point bending tests. And you can see the for plant concrete, there is nothing is going on. So when the maximum stress is reached, the deflection, the beam is not able to carry none of the loads. However, when we add the fibers to the same concrete, after appearance of the first crack, they bridge them. So they bridge them, so they increase the strength, the flexural strength, and then further they increase, they are still able, the fiber reinforced concrete is still able to carry the loads with quite high deflection, or we are also, or deflection, we are measuring all the crack mouth opening displacement, so the width of the crack. So generally, this improvement, it highly depends on dosage of fiber, first of all, geometrical parameters of fibers. This is also very important. Orientation of fibers, because there are some techniques that we can let's say, adapt the fibers and put them in the ways we exactly want them to be. Because it's obvious when we put the fibers here, it will be the pronounced increase of strength. But when the same fibers are put vertically, nothing will happen. So the orientation and of course the strength of the same matrix. And now we will discuss the dosage of fibers and geometrical parameters of fibers. So when we have, of course, if we add more fibers, the higher dosage of fibers, then we will get the higher strength. But when we have the plain concrete, we are talking about civil engineering. So we generally have the elements that have the contrast reinforcement. So this is the test that tells us where we can use it. So when you pour the plain concrete, you can see it goes, nothing is happening. But when we have the fiber reinforced concrete and we have the high dosage of the fibers, this kind of concrete can't be used in the elements with the contrast reinforcement, because it wouldn't be able to get to all the points it should. So this is the first disadvantages. So we are reducing the passing ability by adding the fibers, any kind of fibers. That's why the fibers are usually used for the floors, because then you don't have too much of the reinforcement. And in the floors, they are used to reduce the shrinkage. Yes, because the shrinkage in the concrete appears. So when you put the fibers, it just holds it. Yes, so the strengths, the tensile strengths do not appear. So this is for the best for the floors. And now the second part, we have the slump flow tests. And when you add the fibers, it highly decreases. So again, this kind of concrete can be poured everywhere because it just won't work. So reduction of flowing ability, of course, is connected with the high dosage of fibers. And now, what about geometrical parameters of fibers? So when we have, here we have the plain concrete. When we have the stride fibers, we can achieve, these three examples are from my research, but in some research we didn't get so much increase of strength of concrete. So let's say we get some strength increase, and then for the stride fibers there is no hardening phase. There is only there's nothing going on. So in truth, these fibers we are adding, and let's say they are quite okay, but with no great improvements. When we are the same fibers, when we shape them, yes, we are making a hook ends, or we are crimping there, whatever, then it starts to work because the anchorage is much better of the fibers. So they are not slipping very easily, but they are anchored in the concrete. So we get the further improvement of the flexural tensile strength. And when we additionally change the cross section for much bigger, again, the force on anchorage are increasing. And what about the steel cord? You can see that these shapes, this kind of fibers are produced generally to this purpose. And this is the waste, so we don't know in truth what's inside. Yes, here the parameters are sure, every fiber has the same length, the same cross section. What is the characteristic of the steel cord? First of all, you can see the bigger fibers, the smaller fiber, various length and diameter. It is connected with the process of the reclamation of the fibers from the tires and from the types of the tires. For example, the bigger wires, let's say wires, they are coming from the truck tires, yes, and the smaller one are from passenger cars. So we never know what's inside, what we will get. So the length also, it's dependent of the first phase of the processing of the fibers, so shading the tires. So this various length, various diameter, and some pieces of gum, because it may always happen, these are the characteristics that this encourage the researchers, the people to use it in concrete, because you never know what you get. But from the other side, when we come back to this picture, when you are using one type of fibers, the strength that you get is very predictable. Yes, this is obvious. Yes, for the stride it will be around this, of course, for the same matrix. But when we have the fibers like this with the various length, it works like hybrid mix. So it means that we have it can attract the smaller parts can attract the smaller cracks, and the bigger can attract the bigger cracks. And please remember that, for example, when we get at the 1% of the big crimped fibers, it will mean that we will have some number of the fibers inside the concrete. When we put the steel cord, we have much more of them. So the mix is much homogeneous, because we can have not too many big fibers, but generally in the concrete we have a lot of wires, and it is all over there. So the bigger fibers you have, because of course the best increase of strength is observed when we get the longer fibers. The longer the fiber, the bigger the increase of strength. So here, and then when we get the longer fiber, when we put the longer fiber, then we have the lower number of the fibers in the square meter. So here is opposite. We have a lot of fibers. So this can be an advantage and disadvantage. And now, what was the aim generally of the research? So first of all, we had to prove that there is some there will be some impact on the concrete's material parameters under quasi-static and also dynamic conditions. Why dynamic? Because fiber reinforced concrete is a concrete that is used for the high strain rates. For example, for some impacts, for some blows and so on. So it was very important to do it on both conditions. And secondly, to prove the influence of fibers on the cracking resistance. Why? Because when it improves the mechanical parameters, it can be considered in the calculation of ultimate limit states. And if we prove the influence of cracking resistance, it can be calculated in serviceability limit states. So when we design the construction, we have always two states. Yes, so we have ultimate limit states and serviceability limit states. So we have to provide to the engineers the knowledge how these parameters will change. Yes, what will happen if we add these fibers? Will there be some improvements or not? So what was the scope of the research? First of all, the laboratory investigation, of course, of quasi-static parameters under compression and flexure, dynamic tests under compression, and we made also some tests of full-scale beams, bending. Of course, they were bent to check what's the influence of the fibers on the load-bearing capacity and on the cracking. So what are the tests that we usually do? That is recommended, of course. So the compression test must be done, and the 3-point bending tests that I have already discussed. And what the result do we achieve when we test the concrete and the fiber reinforced concrete? So for the concrete, when you start to compress it, you will get the maximum value. And here, of course, there could be like this. It just splits out after the tests. But when you put the fibers into it, it is still able to carry the loads. But this value is not too high. So even if you add, here is 1% of steel fibers. So even if you add it, it's about 80 kilograms per square meter. It's a lot of fibers. The improvement it's not so pronounced. However, in the 3-point bending tests, we can see the high improvement. So here is the black line. It's a plain concrete. So when you have the test, just as I said, it just breaks into 2 pieces and there is nothing going on. When you have the fiber reinforced concrete, then you can see that after achieving some deflection, or the crack mouth opening is getting bigger, so it's in truth is cracked, it is still able to carry the loads. So here we get about 3, let's say, megapascal, and here with 1 millimeter of crack mouth opening deflection, we still get 2 megapascal. So it's very good. And when we get 1%, it's almost the same, yes? So this is very good. However, it's not as good as in the other types of fibers, I must say. So, of course, we could see some improvement in the residual flexural tensile strength. However, it's not so pronounced. For example, when you add the typical hooked fibers, which are the most popular, you will get here the hardening phase. You will get it here, and it will be much higher. Yes, that's why I think that's why engineers do not look at the fibers, because it's not. They think that it's not worth it, but I will show you that it is. And so let's say its advantages and the disadvantages. It's for sure that we have no improvement of the flexural tensile strength. So in truth, if we add fibers and we don't add it, we have the same tensile strength. So it's not too good. Let's say it's not too good. And what else did we discover? Because this, I'm not showing the results from the different beams. Of course, we have some scatters between the results. However, when we were testing the concrete, we are mainly, the fiber reinforced concrete is the best in self-compacting concrete. Because when you put the fibers, you are just pouring it and leaving. So the fibers, they are placed in some way and it's not touched. But when you have the concrete, it has to be vibrated. So when you pour the mix, then you are vibrating it, and the fibers usually go down. And it's not so good. So these are the examples from our research with concrete. So we get almost no scatters for the very low amount of fibers. But when the amount was higher, the scatters were much bigger. So this is also a huge disadvantage, because of course we have some safety factors, but even if you can see that this difference is quite good, quite big. So for sure, I will say that we shouldn't use it in concrete. In self-compacted concrete is great, but in concrete it's not recommended. And here I would like to show you, because I was surprised by myself, that here are the results from different tests, and they show that it's actually the same. We get no matter of the matrix. Generally, the matrix were quite similar regarding the compressive strength, but no matter of the matrix, we get similar values from completely different laboratory investigations. So let's say we have here 0.5%, and here we have 0.5 from the different research, and it is almost the same. Yeah. And here I have more of these examples, and we also compared the results with the friends from other universities in Poland, and they have different fibers, also reclined, but different from the different producer. Let's say that the matrix was comparable, and we get almost the same values. So this is very good point, but it was self-compacted concrete, no concrete. So this is very important. And now, as I said, we have the improvement, but how big is this improvement? Can we use it or not? So we have to look at the requirements from the Model Code 22. And generally, in fiber reinforced concrete, we consider at first the maximum load at the limit of proportionality, when it starts to be cracked. And then we have the values of the stress that is still able to carry, that the beam is still able to carry for the width of the crack. So we have 0.5 millimeters, then we have 1.5 and 3.5. Oh, no, it's not 3.5. Yeah. So we have to check if it's still able to carry some loads. And it appeared that these conditions, that it have to be the comparison of these two values and these two values, that this have to be higher than 0.4 or 0.5. So it is fulfilled. Almost for every dosage of the fibers, it has to be higher than 0.5. If the dosage is higher, we can use it. According to requirements of Model Code, it can be used in concrete. So we have, let's say, small advantages of application of fibers, but it is enough to use it according to the recommendations. So can we use it? Yes, of course, we can use it. And now, the results that is obvious, I think that everyone feels it, when we have the concrete after the test, yes, it's the results from the concrete, and this is from fiber reinforced concrete. So it is cracked, but it stays still. Yeah. I must tell you that we have been investigating a lot of different types of fibers, also synthetic fibers and so on. And then there are some kinds of fibers that after the test, you can't see which of the test was already tested. The fibers are.
如果把我逼走了，我是不会放过他的。我一定会告诉所有人我们怎么走的。
So, and in 3-point bending tests, when you have the concrete is completely crushed, we have to even put some supports because it can destroy our device. And when you have the fiber reinforced concrete, it stays. The fibers are still keeping it. So this is of course used, let's say, in the floors, but not only for the shrinkage, but for some drops and so on. Yes, so it's used. Fibers are generally used in Poland. I think that in other countries also. And this laboratory investigation shows that the fibers from recycled fibers could be also used. It's the same. Yes, there is no huge difference. And now the bending tests. We have performed the tests of bigger beams. It was a huge part of the tests. I will show you just some part when there was the beams reinforced with longitudinal bars. So we were of course testing the deflection. We were also testing using the digital imaging coloration. We wanted to see what's going on the surface of the beam. So how the strains are developing in the elements with the fibers and without the fibers. So this is the cross-section of the beam and the project of the beam. So this was the part when we usually should see, where we should see the results of usage of the fibers. And what did we invent, let's say? So first of all, we were very surprised, but we, in our tests, I'm always saying that in our tests, we achieved increase in load bearing capacity of about 20%. So this is the huge difference. When we add the fibers, we have the increase of load-bearing capacity. We didn't expect. We expect the biggest influence of the resistance to cracking, not the load-bearing capacity. And here, when we have the fibers, they placed here, they were, you know, we could see, I don't know, I'm not sure if I have it here. They were, when we have the bars, and we have the bars with the, in the elements when there were the fibers, then the bars were, let's say, less loaded in the fiber reinforced concrete for some moment. And at first the fibers were working, were carrying the loads, and then just the longitudinal reinforcement. So it was really surprising. Also, the deflection was higher. So in truth, the fibers, the recycled fibers, can be used in ultimate limit states. So it's great. It was the great information. And now about the results of the strains. So here there was no pronounced difference. Why? We don't know why, but I will explain. So here is the elements without the fibers. So we can see here are the points where the cracks appear. And we thought that the fibers will cause the decrease of the distance between the main cracks. So that, of course, in these elements, you can see here that here we have only the green. And this, when the color change, we can see that the more of the beam is taking part in carrying the loads. So we have here more small cracks, but generally the main cracks are still the same number. You can see it here.
Sorry, Fulvio is asking to share the screen. I think the slides are not clear. I will just share the screen in Teams. I forgot to share.
Okay. No one noticed.
Is it better now, Fulvio?
Oh. Yeah.
Yeah, this is okay.
It's amazing. We are literally thinking Fulvio would be very interested in this,
Yeah.
and then you say Fulvio can't see the slides.
Okay, no problem. So, contribution of the fibers, we notice the contribution. You can see it here, the difference between the beam without the fiber and with the huge amount of fibers. However, it didn't change the parameter that it used in calculations. So we can't, we can't say that the fibers decrease the number of the cracks. So it's not too good. In truth, it's not too good. So in case of both types of elements, there was only one main crack to appear. However, again, we can see the beam without the fibers. You can see that it's the compression part was highly compressed, and in the fiber reinforced concrete, of course, we have also one crack, but this compression part is not so evidently destroyed. And here is the photo. I think that you could see it. You could see how many of these fibers are here. They are very small, but there are really a lot of them. So in truth, they are working. They are working in this element. They are not so efficient because they are not too big. If they were bigger, they're longer, they will be more efficient. But in general, there are a lot of them, and it's very good. And coming back to the rheological parameters of the mix, we can't add more because the 1%, 1.5% is the highest value. Because when we add more, the self-compacted concrete, it won't be able to pour somewhere. Yes, so this is the highest amount of the fibers that we can use. Okay, so it was the quasi-static tests, and now we have performed also the test under high compressive strain rates. Why? Because the fibers, the fiber reinforced concrete is usually used there. So here you can see the generally the strain rate. And here is the quasi-static, here are the quasi-static strain rates, and here are the dynamic. So these are the results from the test that we achieved. And here for the dynamic parts, these are the types of strain rates that are connected with explosions, impacts, tornado waves, tornadoes, ocean waves, and so on. So this is the, of course, the blows. Yes, so the military is using fiber reinforced concrete everywhere, because it is obvious that when you have the concrete, it just splits because it's brittle. When you have the fiber reinforced concrete, he can catch all the energy. So the test that is used is the split Hopkins oppression bar. And one more very important thing. In the test, when here we have the compression strength, quasi-static, under the high strain rates, you can see even 2 times, even 3 times the quasi-static strength. Yes, so it's much higher. And that's why it's the test in general is very complicated. So where am I doing this test? This test I'm doing in the Military University of Technology in Poland, in Warsaw. They are equipped with the Hopkins compression bar, and it's a very long device. It wouldn't be placed here for this. So it is at Military University of Technology, and how it works. It works, we have the barrel, and here we have the striker bar that hits the incident bar, and inside of between the incident and transmitted bar, there is a specimen, and it is just crushed. However, the whole process is very complicated. We have to choose every time to every material. Even from in the same series of research, we have the concrete and we have the fiber reinforced concrete. So we have to choose the exact pulse shaper to get the right results. And the same, the specimen have to be prepared in the special way. We have to assure the exact adhesion of the specimen on the both ends of the specimen area to the bars. If we don't get it, the results are rubbish. So here I would like to show you the test. It's last in microseconds. So now you can see how it's crushed, and to check whenever the test is okay, it's we have to. This is what we get from the machine. We get the proceedings of the incident, reflected wave, and transmitted wave, and then we have to proceed it to check if we have the equilibrium stress state. So in compression test, we are not thinking about it because it takes time, to compress it. It's about for a long cylinder that we have for the compression, because it's 150 in diameter and 300 millimeters in height. So it lasts about 2 minutes, 2.5. So it's very, very long. Yes. So the specimen have time, and that's all. And here in this test, we have to, every time we have to check if it was compressed. Because if sometimes it can be shared or something. So it's this test, it's very, very hard. And then we have to calculate what's really the strain rate. So are we in the range of tornadoes or the impacts? Yes, we have to know where are we. And what do we achieve? We have a very good reparability. So we have, for the same mix, the results are almost the same. That's why we are doing 3, 4, 5 tests. It's enough, because the verses of the diagrams, it's the same. And what did we achieve for the fiber reinforced concrete with the usage of recycled fibers? Here is the typical diagram. And this is the comparison with quasi-static, is the stress-strain relationship. And when we increase the strain rate, it's of course the strength increases, and it's comparable. The results are very similar to the results of other kinds of fiber reinforced concrete. And when we compare it generally with the concrete and with the other results, when we compare it with the concrete, so when we have the concrete, this is the strain rate sensitivity of concrete. So generally the fibers decrease it. All types of the fibers decrease it. So let's say we have the concrete with the very high strength, so it is less strain rate sensitive than the concrete with the lower strength. So here the fiber reinforced concrete is stronger, so it has the lower strain rate sensitivity. So in case of recycled steel fibers, we achieve exactly the same results as we get in other fibers. So it is the same way useful in these applications. And when we compare it with the results from the other researchers with the same amount, this is important because this influence is changing according to the amount, and it's not easy to find the similar research with the similar, let's say, we have to consider also the matrix, the compressive strength of the matrix. So these are the results with the exactly comparable matrix and comparable amount of the fibers. So you can see here that it's very comparable. So it's the same. So there is the conclusion that we can use it. In these applications, we have no limits, completely no limits. It's the same. And what could we also see, considering the failure pattern, when we add the fibers, then for the lower strain rate, so let's say for this 100, about 100, we could see that the specimen was not destroyed. So we can see the fiber pull-out, fiber bridging, and so on. So the specimen was not destroyed. When we analyze the higher strain rates, it's normal that it's crushed completely. No matter with the concrete, fiber reinforced concrete, there is nothing that can stop it. When you have the blows, you can imagine, when you have the blows, no matter what you have, it will blow. So sometimes we can find some cones inside of the elements after the test. So it in fiber reinforced concrete, let's say that for the higher strain rates, we can't see the influence on the failure pattern. So what about the conclusions? What we discovered, what we proved? So first of all, what are the advantages? We achieved the increase in the residual flexural tensile strength. So telling it in the short, let's say, the fibers, when we add the recycled fibers to concrete elements, they are still able to carry the loads. Just like the other types of fibers, maybe not with the same efficiency, but they are still able to carry the loads. And this is very important. We can use it in the calculation of the ultimate limit states, serviceability limit states. We can use it. Increase in the load bearing capacity of the beams. This is the point that is bold because there are a lot of, maybe not a lot of, but there are some research in Europe considering the fiber reinforced concrete with recycled fibers. And some researchers noticed very small increase on the load-bearing capacity, but it was not pronounced enough to consider it. And there is even the belief that the fibers can't be considered in the ultimate limit states because the fibers, you never, there's uneven distribution of the fibers. So you never know in truth, in the critical cross-section, how many of the fibers will be there. And that's why engineers, whenever I talk to engineers and I'm telling them, this is, we could see it. And they are telling me, take it away, take it away. I'm also an engineer. I was also practicing and I said to myself, if I have to sign it, I won't also consider it. Yes, so we have it in the research, yes, but it's different when they have to build it and it have to stay the loads it should. So, however, we have it. And I must say that this conclusion is also very important because we were testing other beams with other kinds of fibers, and the scatters between the results were much bigger. So we get the beams where there was completely no influence, and we get the results when there was a huge influence. So this is connected with the orientation of the fibers. And in case of these fibers, because there are a big number of the fibers in the everywhere, yes, inside of the beam, so we didn't get so much scatters. So this is very important. A conclusion. Then dynamic material properties comparable to other fiber reinforced concrete. So this is also very important. We can use it instead of other kinds of fibers, and it will be the efficiency and the high strain rate will be the same. Resistance to cracking. Here again, in the calculation of the serviceability limit states, there is the parameter of distance between the cracks. We didn't achieve it, yes, but everyone knows when we have the fiber reinforced concrete and we throw something on it, it won't break, yes. So we are calculating it. However, it's not so obvious to calculate it in the. Of course, I must say here, this increase in flexural tensile strength, there are the residual. So for the crack mouth opening 0.5, 1.5, and so on. So this is also the parameter that is included in calculation of the serviceability limit state. So it's the same. However, we didn't achieve the decrease in the distance between the fibers. And of course, reduction the level of destruction in every condition. So quasi-static dynamics, it always reduces the level of destruction. And disadvantages. So negligible influence on flexural strength. Yeah. So this is disadvantages, because when we have the normal hooked fibers, it always increases the flexural tensile strength. So, but there is nothing we can do about it. And this low improvement, it is low, but it can be considered. Yes, so we can't say someone who is buying it that you will get the composite with the high values of tensile strength. You will get the composite with the enough, let's say, tensile strength, and uneven distribution of the fibers. But we notice it in concrete, now in the self-compacting concrete. So it is worth to point out. So. Here you have the sources that I was using, and we got our lab, we got 2 projects to finance this investigation that I was talking to. And I must say that we had also with Taghried, we applied for the European project. We didn't get it, but we get the seal of excellence. So we get for the same proposal, we got 95%, but we didn't get it. So it was we couldn't do it. However, I got 2 projects from the Polish, from the National Science Center in Polish, and from our rector of Silesian University of Technology, and it was, let's say, some parts of this bigger project. Okay, so thank you very much for your attention. I hope you liked it.
Oh, that was brilliant.
Thank you so much. I just realized you did not introduce yourself, and I did introduce you.
No matter.
So can you, just for the record, to say?
Yes, yes. So my name is Malgorzata Pajak. I'm from Silesian University of Technology. I work with concrete, mainly with concrete, and with fiber reinforced concrete. This lecture was about recycled steel fibers, and I'm doing mainly the laboratory tests under quasi-static conditions on materials part and on the full-scale elements, and also in the Military University of Technology in Warsaw, I'm doing the dynamic tests, because in military they are everywhere putting the the fibers and the concrete with a lot of concrete with a lot of fibers. So this is the right place to test it. And here, this photo is from Warsaw. You can see one Hopkinson bar. There is the second Hopkinson bar, and this is the number of the specimens that we have to test to get some results. Yes. Yeah. So this is all, I think.
Thank you.
Thank you.
So I think we should open. Fulvio has his mic open. Did you?
Do I?
Oh.
I didn't even realize. But anyway, I wanted to ask a question anyway.
Yeah, go ahead.
So first of all, sorry, I really wanted to join the meeting, but I was teaching until 25 minutes ago. So I got stuck in a class. So I missed the beginning of the presentation. So perhaps this kind of question may be stupid, but I'll ask it anyway. I missed I'm sure you discussed about that. I missed what's the percentage of the recycled fibers you put into the concrete? So in weight.
Yes, I will show you. What kind of fibers were used? Yes.
What percentage?
What the percentage? Yeah.
Percentage were different from. I will show you the.
Malgorzata, the presentation is not being shared at the moment, so.
But I think you can still see the slides.
You can still see the slides?
Can you see the slides, Fulvio?
Not really.
No.
You can see the screen, but it's not. Can't really read it.
Sorry. I stopped sharing the screen, that's why, sorry. I was hoping you can see the camera.
No, we can, but we can't really see it. Okay.
Yes. So here you can see all of the part that I told you about is made of many research, because I have been searching it from doing this laboratory research from 2014 maybe. So there are a lot of tests, and here you have, for example, the results where you have the dosage from 0.38% to 1.5. The higher dosage, for me, it's rather impossible to add. My colleagues told me from other university that they managed to add 1.75, even 2%, but it was only to pour it into some slab, and that was all. Because the fibers, when you see I will show you the characteristic of the fibers, yes. So the fibers there are various lengths and diameter and so on. So there are a number of fibers inside of the mix. So when you get, I have to make the photo when you have the 1%, so about 80 kilograms per square meter of hooked fibers and of these fibers. These are a huge amount of fibers. It's weight the same, but here you have just few elements, and here you have a lot of fibers. So in the concrete, it really fulfills it. Yeah. So the higher dosage is it's really hard to obtain.
Okay. And the length goes between 5 and 70 millimeter. I can see. So I joined also for the last bit with the Hopkinson bar and the high dynamic test. Have you studied, or are you interested in studying the effect of these additional fibers into the damage propagation mode? And I'm talking in particular on crack propagation, and so for, let's say, barely visible impact damage, or crack corrosion, something that basically is not a pure explosion, but to check if the presence of the crack is actually acting at the tip as stress intensifier, for example. Because I checked just the final slide in which you were saying, if I'm not wrong, that the increase in some of the mechanical properties is not really measurable. Am I correct?
Something was on
in the disadvantages, yes.
Disadvantages. Okay, so maybe from the first part. Okay, when you have the Hopkinson bar tests, this increase. This is more complicated, let's say. But as you can see here, here are the results from the compressive strength quasi-static, and here you have the dynamic. And you can see that here we achieve even 2 times the quasi-static strength. And first question is, why do we achieve in concrete 2 times the quasi-static strength? And it is still let's say the discussion about what is really happening here, yes, what's going on. So we already made, I have here the computer so I can show, we already made some tests because when you compress it with the very high strain rate, then it in truth it blows in the radial direction. So when you have the radial forces, this forces causes the compressive forces on the specimen, yes? So, and concrete is the material which is highly affected by the compressive strength in 3 dimensions, yes? So one of the theory is that in truth this increase is connected with the contribution of the radial forces that appear during the dynamic tests. Yes, so so this is the first let's say part of it, and considering this, in truth it is hard to find the influence of fibers, because maybe some other issue also. So we are now starting to discover what in truth in test, because in test, when for example you are doing a numerical simulations, you achieve this value without you say, let's say you have the big elements, you are putting there the concrete, the blows, and you achieve this value, yes? When we have the small elements, without adding to concrete, you are using this compressive strength from quasi-static. And in the result, you achieve this. And here we are testing the material properties. So we are testing the small elements. So in truth, if you put to the numerical simulation this value, you will achieve it 2 times higher. Yeah. So let's say this it's complicated. So we are not able in the tests to achieve the value that are not affected by the contribution of radial. It is called radial confinement. So when we have the big influence of this radial confinement, we are not able to test the influence only on the fibers. The only results that we are sure of, I will show you, it's that the fibers. This is this DIF is the comparison of the dynamic strength to the quasi-static strength. So we have this huge increase for concrete, and for fiber reinforced concrete it's lower. So this is for sure that we achieve it, no matter of the radial forces and so on. So we are let's say
it's lower, but the gradient seems higher. So it seems to me that the effect of the increasing strain rate, it's higher for the fiber reinforced concrete than for the normal concrete. Or it seems that the gradient of the light blue curve, it's higher than the one for
yes, but this, yes, but you can see there are only few results here. Yes.
Yeah.
You need to have more to see. But generally, all types of fibers causes the decrease. Yes. So we causes the decrease. Of course, for the lower strain rates, you can see that the level of destruction is lower and so on. This is the only thing that we can be sure of. Yes, the other parts, how they really influence, is the stress on the tip is changing and so on. We can we can discuss it on the quasi-static tests. Okay, we can do it, but on the dynamic, it's impossible.
And on the quasi-static test, have you done it, like studying the propagation of the crack at a microscopic level?
No, macroscopic level, no, because why not? Let's say I've done a lot of tests of fiber reinforced concrete.
Yeah, okay.
And it's generally all kinds of fibers work the same. So they do not work till the concrete cracks. There is a little influence on the first crack strength. So it's impossible because, you know, for concrete, very little strain, the very little strain you get, the concrete is crushed. And the fibers, it doesn't know that there is some strain, yes, because of the differences in the modulus of elasticity. So all the fibers act the same. They start to act after the cracking of the concrete, yes, and then they, of course, they yes, it is connected with the process of bridging and so on and so on. They all act exactly the same way.
Okay. Very interesting. I've done. I mean, I'm an experimentalist as well, so
okay.
I'm very familiar with the struggle of getting good data.
Yes, I think I know your name. Yes, I think now I'm looking now. I think I know.
And I work mostly with composites, so fibers are.
Yes.
I'm quite familiar with these issues. I mean, I totally agree with the frustration in getting data sometimes. I was wondering if you had any idea of what do you think it may happen at the microscopic level to see if, because you have a large distribution of length of fibers, of course, coming from recycled sources, and I think that perhaps it would be interesting to try to reduce the length and be specific, because you may have that the critical length of the fiber may actually change and swap between being an advantage to a disadvantage. So if you filter, for example, all of your fiber, and you say, okay, I keep only the long one and I remove the short one by sieving them, I have no idea how, perhaps you can get better results and remove this negative effect, because it's clearly interesting that you have this sort of plastic behavior of the of concrete, which would, in terms of stress distribution and energy absorption, would change a lot. I mean, you have an increase in energy absorbed here, which is massive. And while it doesn't mean, in my opinion, that the structure still can be used, but it gives possibility to prevent any critical collapse, which is very good. Yes. And it can also be an alarm for doing reparation. So it makes sense to me. It is very interesting. Perhaps controlling the length, the specific length of these critical fibers, of the reinforcing fibers, may actually improve this thing even more. Because an increase of 1% or 0.5% in weight is acceptable if it gives you this advantage. So very interesting.
Yes, talking about the length of the fibers, it's hard, because I knew the people from the company who were invented some new technology to process the fibers, and it was very, very cheap. And I asked them, do they have influence on the length of the fibers? And they told me that at first part, they are shedding it into some elements, so they can choose the first length of the scrap, yes. Mm-hmm. But then when they do the other kind of the process, they didn't want to tell exactly what. It is somehow also can be cut, and they told me that the wire, it has a very high strength, because it's the best steel used in the tires. So they told me that it is generally, the process is very complicated, and when they remove all the very short fibers, there are some parts of some parts, yes, that almost nothing left. Yes, so they told, for them as the producers, it's worthless. So it's better for them to produce this in one piece, and than to take out just the bigger fibers, because sometimes it can be seen here, but sometimes there are twists with each other. Yeah, and that would definitely create a stress intensification point. Yes, crack generation. Yeah, you can see it one on the left, I think. Yes. Here is, I think, something. So it works like this, but generally I'm surprised that we achieve a very small scatters between the results for this mixes, because the bigger fiber I tested, the bigger were the scatters. for example, for the biggest hooked fibers, okay, the performance was very high. So the hardening phase was very high. The increase 2 times of the flexural and tensile strength. However, it was in one specimen, and in the second specimen, it was like concrete because the fibers were not there where it should be. Yes, so and here it was not. It was not because of the different length, because of the small part of the fibers, they were homogeneous. It was the homogeneous mix. Yes, so I think that it still has a right to be used in concrete. And even now, when I was preparing to this, I found some newest review, and I was shocked that so many people started to test it, and they get similar results. So I mean that generally it works like this, and it could be used. It could be used, and it. I said for the slabs or for the application in military, it's great. It's great. It's nothing better.
Okay. Very super last question, because again I missed the beginning. So I'm assuming that the distribution of these fibers is random. So they are randomly distributed. Have you thought about orienting them somehow?
No, it's impossible. It's impossible because they are twisted in different directions. But about distribution, it's a good question. I have thought about it, but if you were not, I will tell you. So this is what happened in concrete. So when it was vibrated in conventional concrete, that's why after this research, we started to use only self-compacted concrete. Because when we, for a small amount of fibers, of course, there was completely no difference between the results. But when we get more than 0.5, it's the scatters were pronounced. So I think that it is connected with the vibration of the concrete. So for the self-compacted concrete, the results are, let's say, as for a fiber reinforced concrete, they are quite okay. But here, the scatter was really pronounced. So I think that they are, I can even show you, there was also one more photo. Oh, here. Here you can see the distribution. They are placed everywhere. This is for 1%. Of course, here they are, yeah, but this is quite good photo. When I made the photo, you know, when I turned the beam, nothing could be seen because it's, but this one is quite okay. You can see that there are a lot everywhere here. So the distribution of this kind of fibers, I think it's very good.
Thank you.
Thank you. Thank you for
It was a very nice discussion.
Well, that was brilliant. I mean, and this is, I was just about to say, it's one of the nice things about these new research centers, because Fulvio is not in this. I mean, are you guys, which department are you guys in? Chem Eng, civil engineering. So this is the point, you know, you get people who are in quite different disciplines coming together to engage on a topic. I just want to congratulate you on a fantastic talk, because you start from the story of how extracting these fibers and, you know, the sort of broader resource implications and so on. And then this amazing series of tests. You've obviously spent many, many years developing these data and convincing people that actually you should be using this. So it was a really brilliant talk. So thank you for coming.
Thank you very much.
It's been a wonderful experience listening to you.
Thank you.
I have to say, I know nothing about materials. I don't know anything about concrete. So anything I say or ask, you have to sort of mentally discount as coming from a 5-year-old child or something. So I think you've actually partially answered this question in response to something Fulvio asked. So this Hopkinson test, I'm guessing it is impossible to replicate this at a larger scale, because you're really looking at a specimen, and obviously, given what you've just said about the distribution of these things and the fibers being randomly placed and so on, it might be that the blast response at a macro scale mightn't be the same as you would expect at this specimen scale.
Yes, so I must tell you that I have made some bigger slabs, and there are still at Military University of Technology waiting for the test, because we just wanted to shoot to them, yes, to see how it works. However, my friends from Czech, from Prague, they made the tests, and of course they achieved the results that we expected. That's why they are still lying there. It was highly improved. The concrete was highly improved with the fibers. Yeah. So the bigger scale elements can be you can just shut to them, you can blow them, you can blow them. The friends from Germany were blowing everything. So you can see the impact of fibers, of course. Yeah. But to make the Hopkinson bar bigger test, you have to increase the diameter of the fibers. And when you increase the diameter, you increase the length. However, this question is not so bad as you think, because in truth, we have the specimen with the 40 millimeter diameter, and this size of the element requires some smaller, much smaller, 3 times smaller size of the fiber.
Fibers, yes, yeah, so it's been scaled.
Yeah, so in truth, when we have 70, it's not fulfilled. However, there are twists and so on. So even in Hopkinson bar, on some small specimens, we achieve a very good reparability of the results. So I think that this also shows the advantages of these fibers, that they really make the concrete homogeneous. I was previously doing some tests with short fibers, but straight. I was doing it in Dresden, in Poland, at Military University, and the results were not good. Not good. We have published something, of course, but I must say that the results were not good, because it was highly affected by the position of the fibers. So in truth, we can't test it in the bigger scale. The material properties can be tested in the bigger scale. It should be bigger, just the Hopkinson bar. Of course, the people who are involved in modeling, they are looking at the research. Oh, it's not so good. But when we get the same reparability, the very good reparability of the results, and we can see, and many people around the world, especially in China, they are highly advanced in the Hopkinson bar tests, and we get similar results. So it has to be like
very
this.
Reassuring.
Yes.
Very reassuring.
Yes.
Indeed.
So.
Yeah, but don't pull yourself down as somebody who dabbles in a bit of modeling. We know just how good these models are.
No, I met some people so advanced in modeling that I said, but okay.
You can convince yourself of anything if you wrote the right model. The other thing, it's sort of related to what you just said. You were talking about trying to convince a practicing engineer of the value and utility. So presumably the next step for you would be to actually build something at full scale and show that, yeah, it actually does work.
I have maybe not. I'm maybe not disappointed. It's not a good word, but I stopped to do this quasi-static tests, and now I'm only involved in dynamic tests, because in Poland they don't want to use it. I was talking to different engineers, even my husband is an engineer, when I'm telling him, add this, he's watching at me, and how much is it? No, it's very low cost, but no, they are not adding it, so he won't add it. And I had just some contact with the people who are using different kinds of fibers. And for example, in Poland, for the slabs, they are putting a big hooked fibers, because when you have the slab, you have 20 centimeters, and when you are putting it, it really works. Yes. So this kind of fibers are for some special applications. It could be for the smaller elements when the advantages could work. Yes. And for the slabs, no, it maybe would decrease of course, generally it is, when you calculate the slab and you add the fibers, it decreases, yes, but not in this case, let's say. And for example, I had with some companies who are adding fibers to every kind construction, but they are at the sea. So they are adding to concrete synthetic fibers because they want to have the durability, they increase the durability of concrete. Yes, so that kind of fibers are used in Poland, and other kinds. It's very, very difficult to use it.
Sounds like you need to move to China or something, and that's where you could
No.
do that. The other, sorry, I've still got one or two more, if that's okay. The process of extracting the fibers, there must be a carbon cost to that. I mean, there's a cost,
yes,
but there must be a carbon cost.
Yes.
Have you considered some sort of whole life carbon type analysis saying, well, actually, this
No,
is...
it's not my part. It's not my part.
Yeah. I think that's another area to, which is because that will really, I mean, assuming that it all works out correctly, it will add a whole new dimension to saying, well, actually, this is part of the carbon strategy. Because we can prolong the life of structures or improve their strength or whatever. And because we're simply extracting the waste material at low carbon cost, and not just low cost, it's low carbon cost, actually it makes even more sense than trying to produce. Presumably the existing hooks and things have to be manufactured, right? So you could do a comparative analysis. And I think that, I mean, even if you don't have the expertise that people here in this department, you could obviously...
But the tires, they generally have to be recycled, and they will be recycled, but there are no other option. So this, as I also showed here, among the applications in civil engineering, you couldn't find the application of steel cord. And this is recovered somehow from this. This is recycled. So that's why I choose this topic, because they had it. Right. They had this cord. Yes. Because the cramp, the rubber is much more important for them, because there's a lot of this rubber, and it's natural rubber also, and so on. So they are using this rubber. So this steel cord, it is there.
It's actually a waste product.
It's a waste. Yes, it's a waste for them.
So that's even more brilliant, actually, because it's just. I know you also said it's actually high quality steel they put into it. It's not, yes. So that's wonderful. So the last question, it's not really a question for you in a way, but presumably you've met Kevin and Anthony. What? Okay, so Kevin is our concrete technologist. I'm the director of this research center, which is Renew. And I think a lot of your work is really sings from the same sheet as members in Renew. But Kevin runs another center called, which is, what is it called? Climate and Environment, or whatever. But he's a concrete technologist, okay? And Anthony, he's a structural engineer, and he's been part of Eurocodes and things like that. And a lot of his work has been fiber reinforced. I think that's really the preservation and elongation of the structural life.
What's the name?
Anthony Darby.
When I see that.
Probably, yeah, you probably heard of him for sure.
So, I'm emailing them now to see if they're free for a quick flash, maybe.
Yes, I think you're here till when?
Today.
Just today?
Today, just
today.
She's in the UK for three more weeks.
Okay.
We can get her back, but we need to invite her, I think.
Well, even if it's, even if a Teams call could be a little overhead way of making that, because it's only 2 or 3 people.
Yeah.
I mean, I'm glad Fulvio was here, because that was the other person I was thinking of that you must meet, but obviously you've had a great interaction with Fulvio already, and hopefully you can continue that over a longer period of time. And he's working a lot, he's a mechanical engineer, he works a lot on sort of fibery type thingies, he'll tell you at great length when you meet him. So, but again, you trying to use biological waste products in these sorts of applications. So there's a sort of resonance between the sorts of things you're doing. So yeah, thank you. I think it's been really wonderful. And I think there's a lot more to do with you within Renew, and maybe even slightly outside.
The part of the life cycle impact assessment is a brilliant idea, because if that wasn't done yet, that would be a great area to tackle. No one has done this assessment apparently. But you saying it's already a waste, and
It's a waste, yeah.
that is a positive thing in
Yes, yes.
in this side of
As
the
in,
world.
it's already been generated, it's ready to harvest.
Yes.
You could do it the other way around, which is if you're comparing it against the crimped or the hooked thingies, which are presumably being manufactured,
Yeah.
you could count that as a negative cost in here.
Yeah.
In other words, that carbon cost is saved
Yeah.
because you're reusing it, and if you can show that it's more or less the same for certain applications,
Yeah.
well, actually, that's even better.
Yes, yes, you said the right thing. Now there should be someone who will look at it from this, let's say, financial part, and see.
Financial and carbon
And yes,
services.
and yes,
Yeah.
yes, yes. And because now I have to look, because now I had no time, but I will search in the literature, because there are a lot of new research in this area. I was so surprised. I have to see what they in details what they achieved, but I think that is the same, because nothing will change. And this is also surprising that I forgot to tell it. We have the friend in Madrid, and his colleague was also investigating the same fibers. So it was completely different producer, because it's impossible that they get from Poland. And I compared my results, and they were also very comparable.
Yeah, I think you showed that, didn't you?
It was from mine and from my friend, but from Poland.
Right.
So we
Okay.
let's say the process of the reclamation could be the same.
Right.
But in Madrid, it's impossible that it
Yeah.
was the same.
Yeah.
But the composition is quite similar, and the results are also quite similar. So no matter what part of the world you have, they are quite similar, because the tires generally are similar.
Manufactured by
Yeah.
a few
Yes.
sort of, well-controlled processes and a small number of manufacturers, really. So
Mm.
so that's fantastic. Really, really interesting. Sorry, the older folk have just cornered the conversation, haven't we? So we should shut up now and let you have a stab at it.
You stole my question. It was going to be about the carbonite.
Damn.
That's my area. I haven't got anything else.
That's your area. So here we
Not
go.
like really.
But this was a very good question. But I'm here at the second man from the Seastone, which is actually is it the European project? This is actually about the decrease of the carbon in producing the materials for the civil engineering. So this is exactly the topic. Yes,
Yeah.
so we have to decrease it. But it's not my part, because I'm from mechanical part. So I will test the material that they will discover with the lower, I don't know how to call it, influence of CO2 activation, of CO2. So this is exactly the project I'm here for.
Brilliant.
So it's good that you are telling me this.
Yeah. So anyway, so if you're already doing that, that's fantastic. But I'm sure there's bound to be opportunities for building. I mean, Taghried is our host here today, but there's many more colleagues I'm sure you could work with. I'm hoping that because we're recording it, we can make sure, Taghried, that we let people know that because you haven't attended, we actually know that there is stuff of interest for you to watch. And it's a fantastic talk, actually. Fulvio's got more.
Oh, no, it was just a very simple question. How long are you staying?
Today, but in London, I'm for 3 weeks.
Okay. So you're staying all day today?
Yeah.
If you are around later, I can catch you up.
Oh, I'm taking her to the charging station after this.
Okay. So I'll pop in there. Let me know when you're there. I'll pop in.
Tomorrow morning.
Oh, she's here. Fulvio, she's leaving tomorrow morning. You can catch her.
Yeah, it would be great. Yes.
Okay.
I had to stay till Monday to see Juliana, but no.
Yeah, sorry, Juliana really wanted to make it.
Yeah.
And she's doing this
And I think it
application
will be
thing.
some connection, because Juliana also works with these
We
materials.
can meet on Teams or something.
You can meet on Teams. It's not the same.
Yes, of course, it's not the same.
Yeah, okay, when you see Fulvio, you'll see why I see it's not the same.
Yeah.
His camera gives their own perspective.
All right, you must be tired. Thank you.
Thank you
Sorry,
very much.
do you have a question?
It's not that hard, but I work in different type of the fibers. I work on the plant fibers.
Okay.
So there is a similar tendency towards sexual behavior. Yes, plant fiber can also increase the flexural strength in some part,
Yeah.
but I noticed there is something that is interesting, that because the plant one is slightly different, is about the modulus, because it increased above the plant factor strength, the modulus tend to decrease a little bit. So the curve is like same and like decreasing later stage. And it's different for the steel fiber. And moreover is because I noticed that when you increase the fiber content, that part of the slightly decreased modulus also showing in the increment of the strength.
Yes, yes, you have. I also have tested some. I'm calling it soft fibers, but I didn't manage to publish anything because I think that concrete is too brittle for some soft fibers. And of course, we also get it when you put the material which has much lower modulus of elasticity. You obtain it. You should obtain it. It's normal. And when you add more of it, you should also obtain it, yes. The modulus should be changed. But and you generally didn't obtain also the increase of flexural strength, almost no, yeah? Or you did?
It increased.
How long were the fibers?
The fiber is quite short. It's around 12 millimeter.
12, and you obtained, okay, but not pronounced increase.
The increasement, because that's another part for the parent fiber. The parent fibers is the deviation between the H result is a pain. But overall, you can increase around 20 to 30%.
20, okay. So I maybe with this modulus of elasticity, maybe I will tell it other way. When you have the high strength concrete, the modulus, I will call it like this, yeah? When you have the low strength concrete, the modulus is like this. So when you have the concrete with the lower strength, then you have the matrix, let's say without any fibers, and then you get these fibers, it should change because you have the lower strength. Because we're also testing the compressive strength of this. So the strength should be lower.
Yes.
Yes, and much lower.
But the modulus is low.
Yes, yes, and when the strength decreases, the modulus also. So it's normal. It should be like this. However, in our case, it was kinetic fibers, but with the let's say composition comparable to some natural, because it's our first test, and it didn't work because the improvement was very low of the mechanical parameters. So and the decrease in modulus of elasticity was high. So it was, and the strength of course decreased. So it was nothing good from it in our case. But of course you can have a completely different material.
May I have another question? Because
yes,
you mentioned about the compressive. I noticed that from the cylinder compressive test we have done, it's a slightly different of breaking patterns. It's like when you test plain concrete, it's like there is a core failure or slip failure that's like the tilted surface.
Yeah.
But when you test about the fiber reinforced one, it's much more like split in the center. The crack occurred in the vertical way, so it's a split failure. And it's quite interesting because it's like for me, I test when I with the fiber one. It's more like there is a clear slip surface that is
shared.
Yeah, sure.
You know, when you compress the bigger elements, you may have it is not forbidden to achieve the shear or achieve the cones. It's the same. The value of compressive strength would be probably the same. Even if the old Polish books, you have the different, let's say, failure pattern. So it doesn't matter if you get, but it would be quite confusing if you have only in case of fiber reinforced concrete, there was only shear. So it would be strange because you should also obtain cones. Yeah.
The thing for that part, I think, is maybe connect to the different fibers percentage, because when you make the fiber, it may not that homogeneous distribute.
Of course, but it should be homogeneous, yes, distributed. So we also had some tests when after the test, and it was completely shared. So and there were the parts where the fibers were and the other were not. So it was obvious, yes. But when you have the homogeneous mix, you may have different patterns. And it should be mixed. It should be mixed. Oh, of course, we now, let's say we are advanced, so we rather get cones. This was I couldn't find because I usually not doing the photos of the concrete, and I couldn't find the photo. I was searching for it, but I have it on my computer. But I have the last photo from very high strength concrete. It was more than 100 megapascal. So we get the cones like this, and here was about 0.5 millimeters, and it stayed. It was like this. Yes, so in concrete you might have everything. I can show you then this photo because it looks really, really great. But I will tell you just one thing. Doing the research is the most important thing, because when you do a lot of research, then you get some conclusions, then you start to think why or so. So the best is of course the review of the literature, but do it by yourself, and then you see these differences. Yes, so do it a lot, because the fibers, first of all, the concrete is not so homogeneous as it should be, and when you add fibers, it's a game. So you have to do a lot of tests and to see how it's going on. Yes, what's going on inside and so on. Yeah, so do the tests. Generally do the tests.
I was really interested to see your point of view, because it's completely going to be different.
Yes, but I loved the presentation because she started from the. I'm an architect, so.
Okay.
Really, but I will say that I think this is one of the few lectures that I've attended and understood everything.
Thank you very much. Taghried told me that the different people are going to be. So I had to take a lot of work to show it, not with the numbers, with the recommendations and so on. And even I forget about the main recommendation, and I put it yesterday because I said, okay, something has to be there. But I tried to say it just increase, decrease, yes, because this is the most important. You don't care if it was 20% in flexural tensile strength.
It was logical, it made sense, and I understood a lot of it. But mostly I wanted to ask about the CO2 emissions, but that has already been covered.
Sorry. No, I have to agree. I think because we often get talks and it's hard to sustain interest across the whole talk, because people are so deep into their own research, and they find it very hard to communicate with clarity to an audience. I mean, people tend to communicate, but to communicate with clarity. I think thank you for putting that effort in. It has paid off.
It is thanks to Taghried. She told me there will be people, they don't know nothing and nothing about the concrete in this no concrete. No, okay, no concrete. Okay.
No, that was brilliant.
Talk about concrete. Yeah. But I think it's great. I think it's very interesting. I hope we will meet Fulvio in the charging station in a bit. Okay. And thank you. Thank you so much.
Thank you.
Thank you very much. Thank you.
I will stop sharing and.
I've been mentally practicing your name as well, so I've been making sure I try and get it right next time.
Thank you, Chimpeng, as well. Sorry, we didn't say thank you for joining. You were the first person to join.
Thank you.
Thank you. Bye.